Hey all, what's going on? So, I think that we're live. Today is day 3, week 1, relearning calculus because I have nothing better to do. So, let's just jump into it. First off, we got a comment, so I wanted to respond to that. Let's see, Paulus. Paulus said in linear algebra number 9, fire, with a little fire emoji. Thank you. I'm glad that you enjoyed it. All right, nothing else, no other comments. So leave comments below, comments, questions, and I'll respond to them at the beginning of these videos. But let's jump into it. Here, let's quickly review the problems that we did yesterday. Here was Taalman 01A, and it said describe each in interval notation. That was pretty easy. Here's the answer for that. Taalman 0127. So one thing that we learned yesterday is Taalman, this book is beautiful as hell, and she organizes all of the exercises to different topics or different focuses like review, concepts, skills, applications, proofs, and then thinking forward. So here's our skills question. Find the domain and range of each function using a graphing utility, blah, blah, blah. All right, so finding domain and range and sketch the curves. So square root of x minus 1, you can see that square root for the real numbers is only defined for the positive real numbers and 0. So this starts to become defined at x equals 1 and is defined onward. The smallest value that it can have is 0 and goes to infinity. F of x equals square root of x minus 1. There's a domain and range. All that stuff. Okay, so pause the video if you want to see those answers and analyze it, or watch me fumble around and write them out and live solve them in yesterday's video. Taalman 0179. So here is the problem statement. This was fun. It's nice to imagine an island full of warthogs, an island being overtaken by warthogs. So it says, create a function, write down a function that models this island of warthogs. Eventually it levels off at 512. So here's like a boring kind of function for that. Y equals negative 1 over x plus 512. And defined starting at 0. Wait, that doesn't make sense. That doesn't make sense. That should have been negative 1 over x minus 1. Because we don't want that to tend to 0, to negative infinity. We can't have negative infinity warthogs. That would be insane. And our function is going to be defined at... oh, wait, what am I... I have no idea. I'm confusing myself. That's not the right equation. Yeah, that's not the right equation, but... That was my secondary equation. My first equation that I wrote down was more like this. Like it's like a little piecewise linear function, because at some point, like we start out with one warthog. At some point, somebody else brings another warthog to this desert island. And then they start mating like crazy. And then they run out of food. And then at some point, there's enough food again. And then this just keeps going up and down and up and down. So you can model it as a piecewise linear function. Or you could have a smooth, nice trigonometric function that goes up and down like a spring or something. But those are like a few different options that you could write down as a model for this warthog island. Taalman 0189, use the definition 02 to prove that the range of the function f of x equals 3x minus 1 is R. So, proof strategy, let a be any real number, then our goal is to show that a is in the domain of f. Then f of a is 3a minus 1. This number is defined, so a is in the domain of f. There's a simple, nice, little, easy proof. All right, and then the last problem that we did was Taalman 0, 1, 97. Just don't look at the blue stuff if you don't want to see the answer. Evaluations for slopes and derivatives. Evaluate each function at the values indicated. Simplify if possible. So, evaluating functions. If f of x equals 4 minus x squared, first we're going to find this function, or this difference. So this is like an average rate of change between, on the interval, between 1 and 1.01. And then this one is like the average rate of change between the 0.1 and 1.001. And then this stuff turns out to be really cool. You can see, if you run through the math, that you get negative 2.01, and you get negative 2.001 in this case. So they're getting closer and closer, like a limit. We're going to get there soon. So today I think that we're going to be working with limits. Now we're in section 1.1.1 because I got bored, but there are also a bunch of other preliminary sections, 0.2, 0.3, 0.4. I don't remember what those are. I think that this is like, I don't remember. It's like transformations and inverses, like inverse functions. I don't remember what the other ones are, but I do remember that 0.5 is quote-unquote mathematical thinking, which is nice. So this is, I believe, like intro to proofs. Like, there's a whole section in this calculus book that's like intro to proofs and mathematical thinking and mathematical arguments. I think 0.4 might be logic, even. And one of them is starred, which I assume means hard, and you can skip it if you're a teacher. But I remember thinking 0.4 was not starred, and I was happy to see that. That's like really, really cool. This book is great. I really like it so far. But we got to keep moving on if we're going to get anywhere, if we're going to get to the kind of calculus that I find fun for myself. Taalman 111, this question, true or false, and why? A limit exists if there is some real number it is equal to. Okay, this time I'm going to be a little bit cleaner, and let's draw a nice cyan line here so I can more easily separate the solutions, and I can copy and paste these problem statements without copying the solutions, or just keep them off the screen. Alright, true and false and why. A limit exists if there's some real number it is equal to. Okay, so let's try to give a very brief description of limits. A function has a limit at a point L at a point, say x naught, or yeah, I don't know what notation they use, but it has a limit if when you approach it from the left and from the right, like for all values near, for all x values near x0, f of x is near L. Okay? This is the squishy definition of a limit. And when I say squishy, I mean that Taalman 1.1 says an intuitive introduction to limits. Okay? So we can contrast that with the next section, which is a formal definition of limits, I think. And then you can see in the table of contents 1.3, it's another one of those starred hard sections, and it's called something like delta epsilon proofs. Okay, so I am going to today try to touch on all three of these various different definitions of a limit. So we're going to start with the squishy quote-unquote limit, and then we're going to get to the formal definition, and we'll see an example of a delta epsilon proof. I don't know if I'll do any problems with them, maybe not, but we'll at least see what an epsilon delta proof looks like. And we are also going to take a look at a few different definitions. We're also going to see, what's his name? Rosenlich's. And we will also see, we could see Spivak's. Daddy Spivak's book, Big Boy Spivak, or Tiny Spivak. What's the phrase that I want to call this book? There's two Spivak calculus books. There are probably more, but two that are relevant here. One is famous, and it's just called Calculus, and it is really a real analysis course, but a lot of people do try to use it as a first course in calculus, and it's meant for a first course in calculus. But it's like a first course in calculus for math majors, for mathematicians. Tiny Spivak is this tiny little book called Calculus on Manifolds, and it's hard. That is only for math majors. That is for advanced undergrads or graduate students. And it's all in multiple dimensions. Everything is defined in Rn. We might also see the formal definition according to this other book I haven't even opened yet, but it's a topological definition of a limit according to Gamelin. Hey, Nelson9, hello, I love your content. I love your chats. How's it going, Nelson9? How are you? Thanks, dude. You like this? It's brand new. I mean, it's a brand new channel. I assume you just mean the math videos, right? I also have a guitar channel that's similar but different. But yeah, alright, cool, dude. Which videos do you like so far? Which ones do you like? Help me make this shit go viral, and how do we get the YouTube algorithm to promote this? Like, which videos did you like the most? And thanks. Thank you. You're the best. Alright, so, intuitive introduction to limits, a formal definition of the limits, and then we'll at least see one delta epsilon proof. So this is going from engineering calculus to theoretical calculus. And theoretical calculus can be called analysis. if you want to give it a different name. But, you know, you do you. Okay, so there's a very squishy definition. The limit of a function is a value that the function approaches from the left and the right. Can we give something just slightly better than, maybe better than like a more formal definition than that is, okay, I'm getting ahead of myself. I'm getting so excited. I'm getting too excited. Let's just write down verbatim, what does Taalman call this? I want to write down Taalman's exact words. I'm glad you love the content. What math are you studying? Have you seen calculus before? Have you seen linear algebra? Are you a science major? Like, tell me more about yourself. Are you in high school? Are you in college? It's good to meet people who like this stuff, because I'm trying to figure out who to tailor these videos to. Do I tailor them to graduate students in math and I'm just working on graduate math? Or do I tailor it to like a wide audience? I like the wide audience approach. That's what I want. Okay, so definition 1.1 is a little longer than I expected. Let's do this. Okay, so I'm gonna take a new page. Apparently yellow has turned into my definitions color. Def of a limit. Okay. This is definition. All right. Definition 1.1 of limits. It says intuitive description of and notation for limits. So I'm just going to say the word intuitive because we got to keep going. All right. It says, suppose f is a function and L and C, okay, yeah, she uses C. L and C are real numbers. Okay? So suppose f is a function and L and C are real numbers. All right? Nothing too crazy so far, but that's setting up for what we're going to define here. Limits. If the values of a function f of x approach L as x approaches, what do you mean by approaches? You know, approaches C, then we say that L is the limit of f of x as x approaches C, and we write limit as x approaches C, f of x equals L. Okay, so that's the notation that we're going to use everywhere. So, you know what? This is not that different than what I just said. I literally just said, if I said verbally, or I also wrote it down, the limit of f at the point x naught is L if for all x values near that point, f of x is near L. Like, if the values approach L as x approaches C, then we say that L is the limit. So, okay. I'm going to give some examples and counterexamples and other things as we define these things. All right, so I have enough right now from that one definition A to give a couple of interesting examples. I already gave a boring example of just a line, but let's make that line just a little bit more interesting. What if it's the same line, but at a point it's undefined? Okay? So maybe, all right, I'll switch to her notation. C and L. C and L. But at that point, it's undefined. How do we build a function that looks like this? Well, maybe this is just the trusty old y equals x line. Everywhere except for that one point. So, well, we can make a function undefined if we have x divided by c. Yeah, whatever. I'm getting distracted by these stupid colors. So we can, if we have division by 0 at that point, then that's a way to make a function undefined. I use the open circle to mean that there is no value at that point. Okay? So x minus c, what can I do? I'm confusing myself. I'm confusing myself. Yeah, I think something like x squared divided by x minus c would work. Does that work? For sure, x minus c squared divided by x minus c, that's going to work. Or if I wanted to simplify, maybe this line is undefined at x equals 0. I'm pretty confident that x squared divided by x, which, yes, you can kind of rewrite and say that that's equal to x, but it's not, because the original function, if you plug in x into this equation, you would, or x equals 0, you would have 0 divided by 0, and this is undefined, right? So it is the same as the line everywhere except for the point x equals 0. Now, what I'm trying to get to is, okay, maybe it is, undefined there, but the limit of x squared over x as x, like for all the values near the point 0, the y value is near the y value is near 0. So, like, the function approaches 0 from the left and from the right. My cats are going crazy. Okay, so that's still a little squishy, but I hope that makes some sense. Any questions? Any thoughts? Drop a question in the chat, in the comment section. So that's one example, or another example could be like a function that's defined at one value at one place and then another value from another, like after that point. For this function, there's like two different y values, L1 and L2, and maybe f of x is defined piecewise as L1 when x is less than some point, and L2 when x is greater than or equal to that point. Well, this function does not have a limit at that point, because it's not true that all values near it's not true that all values near the point C equals either L1 or L2. So the limit does not exist at C, but we can say that the limit from the left, which we often write like a minus, the limit from the left is the first number, and the limit from the right is the second number. So this is like saying that we're checking all x values between C minus some, like within some region left of x equals C, up to the point C. It doesn't need to be defined at C. And this other part is to the right. We're analyzing the limit. We're checking all the x values to the right of that point. Whereas over here, when we don't write either a plus or minus and the limit is equal from the left and the right, we're checking all of the x values to the left and to the right. So I am getting ahead of myself. I'm getting so excited. I'm starting to write deltas, and that's in the next section. But I like to make things rigorous. I like to make things like really, to me, it's more concrete and makes more sense that way. But you can think of it as like the values are approaching a certain y value. So even though the function isn't defined at that point, even if we did define it as another value, maybe it's the value 1, at that one point, like maybe the function is 1 if x equals 0, otherwise it's x squared divided by x if x is not equal to 0. So this function is defined everywhere, and the value of the function, notice, the value of the function 0 is 1, and that does not equal the limit as x tends to 0 of that function. So there are times when the value of the function doesn't equal the limit of the function at that point. So that's cool to know. Okay, so that's a little bit about limits at a point. Next, limit at infinity. It's very good practice for me to try to redefine and explain things in my own words. So I'm practicing calculus. Practicing calculus doesn't just mean working problems. It also means teaching concepts and trying to repeat and review the section and the theory in my own words. The best way to learn something is to teach it. So here we are. Thank you for listening. Okay, a limit at infinity. If the limits, if the values of a function f of x approach L as x grows without bound. How poetic. Without bound. Then we say that L is the limit. L is the limit of f of x as x approaches infinity, and we write this. Limit as x approaches infinity, f of x equals L. Okay. Neat. So what's an example of that? An example of that one would be good old trusty 1 over x, right? We're going to try not to write y. We're doing f of x equals 1 divided by x. We could either take it only from the point for the positive values, or we could also define it at the negative values as well. For this one, the limit as x tends to infinity, as this is what we're defining. The limit as x tends to infinity of f of x is 0, because we're getting really dang close to 0. 1 divided by 100 quadrillion is pretty close to 0. So it's getting closer and closer. So, yeah. That's a limit at infinity. I think similarly we get a limit at negative infinity. Or, no, infinite limit at infinity. Okay, part C, buy the book and read it yourself if you want the full definition, because I'm getting bored. Infinite limit at infinity dot 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 the infinite limit. Oh wait, no, infinite limit. Infinite limit means the number exists, C, but there is no value that it approaches. The function grows without bound, I think. Yep, that's exactly what she said as well. Grows without bound. Dot dot dot. Part D, infinite limit at infinity. Dot dot dot. Values grow without bound as, what does it say? Yeah, x grows without bound. Dot dot dot. Okay, so as x grows without bound, the y values also grow without bound. And if you want that to be a little bit more formal, go get the book. If you want this informal definition to be, if you want to see the exact statement, then get the book for yourself. It's a great book. There's the intuitive definitions, and now we have enough to solve this problem. All right, Taalman 111. Let's get into problem-solving mode. Okay. Before I do that, I'm just going to go ahead and write down not the full definition at all, but just what definition 1, 2 defines. We have the intuitive description. Weird. What kind of definition is that? Intuitive description of one-sided. All right, so now, Taalman defines one-sided limits. Dot, dot, dot. And I briefly alluded to what that would be in this notation as well. Definition 1.3, we define vertical asymptotes. Okay, so we've got a bunch of words, and then these are the cases that define a vertical asymptote. Like when you approach this, the limit f of x grows without bound as the variable tends to a point from the left or the right or both. Yeah. The function grows without bound at a point. From the left or the right or both. And then similarly, in this section, we get horizontal asymptotes. Horizontal asymptotes. And then no other definitions, right? Yeah. All right, now we can get into exercise mode. Sweet. Now let's chill and let's work some math problems, because we're a bunch of fucking nerds in this channel. Right? Say hi in the chat or the comment section if you're also a nerd. We are all nerds. If you're still watching this, like, what, an hour into this video or whatever, you're a nerd. You should be proud of it. Nerds are great. Nerds are the best. Limit exists if there's some real number it is equal to. What the hell does that mean? So I briefly, as I wrote this problem yesterday, I was like, what? That, like, does not compute. That does not compute. What do you mean a limit exists if there is some real number it is equal to? Like, what is it in this sentence? So I can interpret this two different ways. First, I want to say, my first thought was false. My first thought was false. If it is equal to means f of x equals the real number a, then we get the lovely example that I created where, like, x is undefined at a point. That's not a problem. But then if we do define x at that point piecewise, like f of x equals 1, otherwise it's x squared over x, 1 at x equals 0, and then the other part otherwise, then this sentence, a limit exists if there is some real number it is equal to. If the function is equal to 1, in my counterexample, then the limit exists. Well, the limit exists, I suppose. The limit still exists, but it doesn't say, the sentence doesn't say whether the limit is the limit exists if there is some real number it is equal to. Like, what I don't like is that nowhere in this sentence does Taalman define a function. And I wanted to at least write out these definitions because here, everywhere, the definition of a limit is like the limit of a function. We need a function in order for the limit to be defined. Like, it's always the limit of a function. Limit of f of x. So I want to say false on this. And this is the only one I've checked the back of the book on. And it doesn't have a reason why, but I do see that the back of the book says that this is true. So I'm a little confused. If you all can help me understand how this is true. It's kind of like it's a vacuous statement or something, and the truth value of a vacuous statement is true. Like, it just feels like a weird gotcha to be the first question in this section. So, shame on you, Taalman. But if we take it very literally, we're saying a limit exists, limit L exists if there is some real number the limit exists if there is a real number that it is equal to. I mean, that's true because we can, as long as we can, if we're talking about the world of all possible functions, then we can always find a function, maybe the constant function, f of x equals L. And then there is a function for which this limit exists. It's a weird statement. The limit of f of x as x tends to c is the value f of c. That one is false. We've already given a good example of that. The line with the hole and a special snowflake value. The limit of f of x as x tends to c might exist even if f of c does not. Exactly. That is true. It's our trusty, the exact same. This is x squared over x. And then this one was x squared over x or 1. The two different functions. Those are different functions. One of them is defined at that point 0. The other one is not. The two-sided limit of f of x as x tends to c exists if and only if the left and right limits of f of x exist as x tends to c. That is true. And why is that true? So just in symbols, I'm rewriting the same thing. This is not the reason why. And it's even further abuse of notation, but the limit of a function as x tends to c requires both the limit from the left and the limit from the right. And that's because I would say the real reason is that this one is defined as all y values near that point are near another number. And this one is like all values near C to the left, like I'm going to call that left near, and this one is right near. Sneak peek, this is really x or C minus delta, the interval, the neighborhood, C minus delta, C plus delta. This is C minus delta to C, that interval. And then this one right near is C, C plus delta. And then notice that this first one is the union of the other two. So it's really like we need the requirements of all the left neighbors and all the right neighbors. Left neighbors and right neighbors all agree, and yeah. Anyways, enough metaphors. Let's move on. Two-sided limit exists. If the graph of f has a vertical asymptote at x equals 5, then limit as x tends to 5 of f of x is infinity. Okay, yes. And that's true by definition of vertical asymptote. Well, I mean, no. It's false. It's almost true, is the thing. Yeah, it's false. Let's see. Definition of the vertical asymptote includes the case negative infinity. So, for example, a function that goes to negative infinity from both sides. Whereas this statement only has positive infinity. Right? So if we want to prove something false, all we need to do is give a counterexample. Just one counterexample that it doesn't, that it's not true for. Moving on. If limit and as x tends to 5 is infinity, then the graph of f has a vertical asymptote. Yes, that is true. So this is the other way around. True. Vertical asymptote can be plus infinity or minus infinity. Okay, if limit as x tends to 2 grows without bound, then the graph has a horizontal asymptote at x equals 2. No. This is false, because if x approaches a point and the value grows to positive infinity, then this would be a vertical asymptote. False. Because what it's describing is at the point x equals 2, the function grows to infinity. So we gave a counterexample. Whereas and let's go a little further and get some extra credit, whereas a horizontal asymptote has I'll write the horizontal asymptote is x approaching positive or negative infinity. Like the x value needs to grow without bound, and then the y value approaches one value. One. So as x tends, like as x keeps getting bigger and bigger and bigger, then the y value gets closer and closer and closer to some number. Okay? If the limit of f as x tends to negative infinity equals 2, then the graph of f has a horizontal asymptote at y equals 2. That is true. And I'm just going to say by definition of horizontal asymptote. From now on, I'm going to use ASY to mean asymptote because life is too short to write the whole thing. So, by definition of horizontal asymptote. Cool. Done. It wasn't that hard. 1.1.1. Let's go ahead and cross it off in our lovely little table. And I guess with my lazy notation here, we also need to add in the next problem. Cool. Let's take a look at problem 21. And since we are going to work on 21 today, oops. Let's go ahead and give space for 22. While we're at it, let's go ahead and give space for 76. And let's give space for 79. I don't know if we're going to get that far, but hey, no problem in just writing them. Right? I do want to take a look at 21. And then I probably should go, because these videos are getting too long for anybody's TikTok attention span. All right. So, we got... Do I want to go that direction? Do we want to solve another intuitive limit problem? No. I want to get to the formal definition of a limit, because I think that that's more interesting and important. So we're going to do 1.2.1. I haven't written it down yet. Oh, these are differential equation problems. Okay. Uh, 1.2.1, this is going to be related to the formal definition of a limit, and I will be writing out the formal definition as we go, and hopefully we can also get to the scary definitions of limits. Or I could say that for another video, scary definitions of limits. That's a nice title, right? A scary definition of a limit. Okay, so it looks like 1, 2, 1. It might be true that the first problem is always a true-false problem. So far, that's been the pattern in Taalman's exercises. 1.2.1, true or false and why is how I'm going to summarize this. 1, 2, 1. A. for limit as x tends to c of f of x to be defined the function, let's leave enough space for solutions on the right. The function okay, good. Yeah. It is the function f. Okay, so this is really similar to the last section. There's nothing more formal here. So here we have the same example, but we're going to need a stronger argument than what we used in the last section. In the last section, it was like, look at the graph, look at the drawing, and does it look like it's approaching that value? Does it look like it if you look at the graph? That's not a very formal argument. So why is this answer not sufficient? I mean, I know that this is a good example, but now we're going to the formal definition of a limit instead. So let's get some theory in order to give that answer for this. Yeah, we need some theory. Definition 1.5. And this is going to be very similar to what I was saying earlier. I was mixing in the formal definition with the intuitive definitions earlier. The limit which we denote by this notation as x tends to c, f of x equals L, means that for all, previously it was squishy. My definition was squishy. I was using delta, and I was saying that the value is near L. So now we're going to be more precise about what near means and how do we choose that delta. For all, so nearness is epsilon. For all epsilon greater than 0, there exists, I should have tried to do this on my own before cheating, but oh well. There exists a delta greater than 0 such that if x is in c minus delta, ooh, weird. Oh, yeah. If x is in c minus delta to c or c to c plus delta, then f of x is in the interval L minus epsilon, L plus epsilon. Cool. I like it. It's ever so slightly different than what graduate books would say, but it works really well. I like this a lot because I noticed that I was using earlier on, I was using the notation C minus delta, C plus delta. Like, I was enjoying the interval notation, and I was like, why don't I see other books using the interval notation for the epsilon delta definition? And the reason is it's a little cumbersome. This is important here, this union, because we don't know that the function is defined at 0 or at C. It doesn't need to be defined at the point C in order for the limit to exist, like our trusty old x squared divided by x example is undefined at 0, but otherwise it looks like a line, and the limit is 0 at x equals 0. Oh, hey, Patricia, good to see you. How are you? What's up? How's it going? I hope you're enjoying these videos. They're moving fast, and so we're already starting to get to some real calculus in this practice session. Real calculus is when, or I keep using the word real, that's overloaded with real numbers. But calculus really begins when you're talking about limits and the behavior of a function approaching a value. It's about rates of change. We're going to use the limit to define other things like derivatives and integrals later on. Yeah. I hope you're enjoying this stuff, like fellow nerd. Yeah, what's up? All right, let's keep going. So the limit is L, means that for all epsilon greater than 0, for any tiny number, there exists another number such that if x is within the neighborhood, if there's a left neighbor or a right neighbor nearby, for all of the left neighbors and right neighbors and right neighbors, then the f of x, the value, is close. It's near that limit value L. So I'm using metaphors and things, but here is the formal definition. All right, so now that we have this, we can try to show why x squared over x is, we want to show that the limit of x squared over x as x tends to 0, we want to show why that is the limit value 0. So it doesn't need to be defined at the point. If let epsilon be any value greater than 0, then I think that then if x is in negative delta to 0 union 0 to delta, we can handle two different cases, but in either case, the absolute value of x is going to be less than delta in either case. Then we know specifically that x is not 0 by this definition. We can see that x is not 0 because that endpoint 0 is a round parentheses, not a square bracket. So we know x is not 0, so we can, x squared over x, we can say is equal to x. We are allowed to simplify this function because x is not 0. What am I looking for? We want the difference between wait a minute. Then I don't think Taalman would have wanted like a full delta epsilon proof for this example. That is the next section, but again, this example definitely is one that satisfies or that disproves this claim. The function f must be defined at x equals c. Like really, I can say the function f needs to be defined at c is not true because it only needs to be defined in the interval negative delta to c union c to delta. So we're close on all this stuff. We had it's really like the if f of x minus we want to show that the value really we want to show that f of x is near the number, the limit value L, meaning, yeah, I don't know. That's going to be the way that works. The metaphors you use are so helpful. Other math teachers should learn from you. Well, thank you. That means a lot. I appreciate it. Yeah, I think it's good to have metaphors in lectures, and like some of the best teachers I learned from would use metaphors all the time, and the lectures would be pretty hand wavy, meaning like, you know what I mean. We don't need to write down the exact formal definition of everything. Like, it takes too long to write down everything super rigorously on the blackboard, on the chalkboard. Like, so some of the best teachers would speak more metaphorically in lectures, and then trust that you'll read the formal, rigorous, precise definitions in your textbook. Both are necessary, and they would expect you to be precise and rigorous and fill in all the details on your homework. But in lecture, you can speak more metaphorically, and it's a better way to teach. It's a better way for a concept to stick in somebody's head, I think. The best way to learn something new is to connect it to something we already know. Absolutely. Yo, hey JB Music, good to see you, man. Have a few minutes between meetings. We're trying, just so you see this, we are today, the goal is to write down definitions of limits. So Taalman, this book is beautiful. It is it's freshman calculus, but it is written in a math major style, like super logical, super clear. Doesn't shy away from delta epsilon proofs even. You suggested Lobster book regarding metaphors for jazz improv. Great book, and that you agree metaphors are the best. It's the best way to learn a concept and have it stick in your head. So, like in Taalman's book, she has a section that's the intuitive definition of a limit, and then there's a formal definition of a limit. And so now I'm trying to do one problem for both of those. And if I can get to it, we're going to get to the scary definitions of a limit. We'll get to the scary ones from this book and this book and this book. That might be tomorrow. That's a great title, right? Scary definitions of limits or something. I like this one. I mean, it's neat. Like, I like the interval notation and everything. And the question was like, does the function need to be defined at the point? And it doesn't. Like, really clearly, the definition has the point C omitted from that interval. Yeah. Okay. And I started writing things in terms of, like, absolute value notation, which is a slightly scarier notation, I suppose. But yeah, that Lobster book is terrific, isn't it? Like, it's very, very good for jazz metaphors. I remember the one, Fresh Lobster. That's the one, like, it's the title of the book, so it makes sense that it's the most important one. But, you want to practice licks. You want to practice, like, ideas, concepts, or something, or scales. Like, you want to practice little jazz licks at home, but then don't come to the jam session actually scripting out, like, I'm going to play this lick, then this lick, then this lick. You have those in your arsenal, and they're ready to pull out at any moment in the middle of a jazz improv. So even though you've practiced licks in the past, like, your employment of those licks is truly improvised. I think in a sense that's what we're doing right now. Like, I'm practicing my licks, like my little metaphors that I'm using. I'm practicing, like, giving, like, weird little rough around the edges calculus lectures and stuff. All right, part B. We can calculate. We can calculate. Where are we? A limit of the form limit f of x as x tends to c simply by finding f of c. So, I mean, so far, this is a hard... I don't know. So far, these problems, these true-false problems, are the same. We can still answer from the intuitive definition. And that's false. Again, our trusty f being either the number 1 or x squared divided by x. That's still a good counterexample. So that problem is false. Part B. Part C. If the limit of f of x equals 10, then f of c is 10. Again, this is the same. I just wonder if she wants us to be writing it in more clear, rigorous counterexamples. I don't know. Yeah. If I think so, I think I'm missing the point of these problems right now somewhat. But you know what? Life is too short. Let's keep going. We will get actual epsilon delta proofs as we go. If limit f of x equals 10, then f of c equals 10. Okay, no. Again, no, that's not accurate. Let me try to write it for this one. False. We need a function where the limit is 10, but then the value is not 10. Let's define f of x as, well, 10 at x not equal to c, and 0 at x equals c. So again, we have this this function that's a simple line with a single point that's different. Oh, I got that backwards, didn't I? So the value is 0 at this point c, but then the function is the horizontal line f of x equals 10 everywhere else. Then let's try to write an argument for this. Then again, we're going to be talking about neighborhoods at this point. So we want for any I guess what I want to show is that this function does have limit at x equals, as x tends to c, the limit equals 10. And I want to show that it is true, what I'm writing down. Yeah. Then and what's tripping me up is that to really prove that this is true, we need to do a delta epsilon proof, which is then the next section. So I'm like, well, wait, how rigorous do you want me in this section? Because to write it, to really do a proof on this, we need the next section, which is marked as optional. Anyways, let epsilon be greater than 0. So epsilon can be any tiny number. Let's give it a different color so that we remember somehow that where the epsilons are and where the deltas are in this drawing. Just imagine the axes, y'all. Just imagine them. You know what an axis looks like, right? Let's use white. Okay, so in this small interval, this is L plus epsilon, some tiny, tiny number, and L minus epsilon. We have this small interval of y values. L minus epsilon to L plus epsilon. I don't know if that's helping or not. And what we want to do is we want to find any neighborhood, left and right, of the numbers of the number of the point C. So C minus delta union C plus delta. C minus delta to C union C to C plus delta. So we fix one epsilon. We choose any tiny number bigger than 0. So 0.00001, whatever. And we want to find a delta, another delta greater than 0. I want to prove I have some neighbors that agree that the value should be L, even if the value isn't actually L. We want to find some neighbors to the left and the right. Such that we want to find some, maybe a neighborhood, like a space around, like within my neighborhood, all of the neighbors within my neighborhood agree that this function should be 10. Like, you want to find your friends. You have enough friends in your neighborhood, and your friends agree with you that the number should be L, such that all x in C minus delta union. Oh wait, C minus delta, damn it. C minus delta to C union C to C plus delta. That f of x minus L, the absolute value of the difference is less than epsilon. That's how I'm used to writing it. And how does Taalman write it again? Yeah, f of x is between L minus epsilon and L plus delta. So f of x is between L minus epsilon and L plus epsilon. Okay, so x is not C. Notice, x is not C, so f of x equals 10 by definition. The function is 10 everywhere other than the point C, right? And so, and it is true that 10 is between 10 minus epsilon and 10 plus epsilon, right? For any positive number e, epsilon, 10 is in that range. Therefore, the limit as x tends to c of the function that we created is indeed 10, even though the function value is 0. So there's like a little epsilon delta proof. which is the next section, which is optional. So I don't know how Taalman wants us to answer these without doing the whole proof. All right, true or false? If f of c equals 10, then limit as x tends to c, f of x equals 10. Well, that's false again, really, by an extremely similar argument. It's like, it's the same argument. Use it, just keep using these, like, here's another little answer. It's the same argument. Do the same thing with what are, if f of c equals 10, then the limit is 10. In this case, we flip the two. Yeah, it's the same damn argument. It's just that we swap the cases. I think part E. Okay, a function can approach more than one limit function can approach more than one limit as x approaches c. Depends on what you mean by approach, because, yeah, we can have, I think that's true if we're talking about like a left-hand limit that doesn't equal the right-hand limit. And this is this is horrible. This is so little space. I'm not being nice to you all. Maybe it's a function that is one value for the negative numbers and one value for the positive numbers, right? The limit from the left is 1, the limit from the right is -1, as an example. So, yeah, I'm going to call that one true. Although the definition, formally, the definition that's written in this section does not, I don't think, define, oh, it does. It does define one-sided limits. Yeah. And it's exactly like how I was writing it before. Which is great. It makes me feel good when I know math. Definition, let's see. Yeah. Definition 1.7 is one-sided limits. And here we have the left limit So we have a definition of a left limit. If x is in the left neighborhood, c minus delta to c, then f of x is in what's the metaphor that I'm looking for in this? I don't know. Like, are the neighbors taking a vote? Are the neighbors like voting on the president or something? Yeah, I feel like maybe neighbors are voting, and you just ask all the neighbors to your left, and if they all vote one way, and all your neighbors to the right vote another way, then the limit, there is a single limit. Otherwise, you have one-sided limits. The neighbors to the left vote one way, and the neighbors to the right vote a different way. Then you have two separate limits. I've never thought of that. I kind of like it. I think it kind of works. So voting is the value in this metaphor, and the neighborhood is a physical space, and your neighbors are the points in that neighborhood. Does that make sense? I could probably come up with like specific states in the United States, maybe, where, I don't know, Colorado or something is neighbored by a blue state to the left and a right state to the right. I don't know. Yeah. And then similarly, we get the right limit. Dot, dot, dot. And the difference is that the neighborhood is going to be numbers bigger than C. Okay. So that's cool. That's some of the notation that I was using when I was explaining the intuitive limit. So that's neat. Theorem, definition, limits at infinity, etc. Okay, so a function can approach more than one limit as x approaches c. I think that we want to consider true. Left and right hand limits can be two separate limits. F. If limit f of x equals 10, as x tends, if x approaches 4, then we can make, this one's weird. Yeah, we can make f of x as close to okay, this one's false. And it has the x and y values kind of swapped. It would be true if we said we can make the value as close to 10 as we like by choosing values of x sufficiently close to 4. So it got this 4 and 10 swapped. Those two are backwards. So, yeah, it's false. G. We're so close. Here, I guess I can move. I can do a fancy magic trick, can I? Zoop. Let's grab this big definition and move it down a little bit. I think we may have enough space, but we could just move everything to the next page if we need to. There's only 2 more left. Part G. Oh, wait, no. EF. Yeah. Okay, so if the limit of x tends to 6, f of x equals infinity, then we can make f of x as large as we like. By choosing okay, so it's kind of like gerrymandering. Like, I never thought of that before. It's like gerrymandering. Like, if you're in control of the political map, of redrawing the political map, and you want of a state, and you want to redraw everything so that that like you can find some redrawing of political lines in a state to equal so that everybody votes one way, like then the limit equals that political result. Like, that's kind of interesting. So all right, let's on this one is true. So if a function blows up and tends to infinity, if it approaches infinity, then no matter what humongous number you pick, I should use different colors, shouldn't I, over here? Let's start using different colors. What the hell am I doing? If you want to find Graham's number, or like just some humongous number, you can do the gerrymandering of this. You can redraw political lines to be small enough. You can find some small number around 0, so that you get like a humongous number for every x value within that neighborhood. That means, yeah, no matter how many zeros you add, and you pick a humongous number, you can draw a small enough political map so that every single neighbor votes on 100 quadrillion. You know? Something like that. H, if the limit as x tends to infinity, f of x equals 100, then we can find values of f of x between 99.9 and 100.1 by choosing values of x sufficiently large. No. I mean, I'm just trying to understand what this what this one is saying, but I think that this one is false. Um, we can choose that the constant function f of x is 100, and then but we can't find any x such that f of x. So it said values between 99.9 and 100.1, but we'll never find 99.99 in this example. We'll never find 99.99. So it's like kind of getting the definition backwards. Like, this is all concepts. This is really just trying to get you to practice this definition, the formal definition of a limit. It's that for any epsilon greater than 0, the y values, that you can find a tiny neighborhood where the function that's an awful drawing. That drawing is more confusing than it's valuable, but you choose one epsilon greater than 0, and those are y values. So here we have L plus epsilon and L minus epsilon, like a neighborhood around the value L. That's kind of cool. Yeah, the gerrymandering example kind of works, I think. You choose one tiny number, like 0.00001, and then the game is to find some delta you choose one epsilon, and then based on that epsilon, you find a neighborhood. You do a gerrymandering such that everyone within that neighborhood votes within that range. I don't know. Such that for all neighbors in X, here we have C minus delta and C plus delta. Okay, so I've rewritten the definition a few different times. I'm getting it into my muscle memory, and I'm able to state it again and again a little bit better, which is a point of this concept question. I think that that's a good place to stop for now. We didn't get to the scary definitions. But we will tomorrow. Thanks everybody for watching. My name is John. I am the math hobbyist. I'm doing this for fun. No, you know what? I lied. I want one more problem. Because that was a concept question. Let's do one more problem. Yeah. I want to see the first skills question from Taalman in this section. 1 point... let's do the intuitive introduction to limits. Because we'll do more formal limits tomorrow. 1.1.21. This is a skills. We did a concepts question, and now we're going to do a skills question. It says, sketch the graphs of functions that have the given in exercises 21 to 30, and there are multiple correct answers. So 21 has limit as x decreases without bound, f of x equals 3, and limit as x tends to positive infinity, f of x equals negative infinity. Okay. I'm going to say that a solution for this problem could be one solution could be the number 3 if x is less than 0. And we want something that goes to negative infinity as x increases. Maybe it's negative x if x is greater than or equal to 0. So the function is positive 3 for all negative numbers, and then it is y equals negative x if x is greater than or equal to 0. That would be a function with those two limits. I keep cheating. You may not like the fact that that's a discontinuous function, but whenever you're coming up with examples, just please try to pick the simplest example you can think of before choosing something complicated. Because if you're watching this, you're probably going to go into programming, and down the road, fancy, complex answers to programming problems is a bad idea. Do not do that. Pick the simplest damn thing possible, always, because your future coworkers will thank you for the fact that they can read your code and understand your code This is a way simpler example than something else. But if we do want to show off how smart we are, or try to get a promotion or whatever, we could probably come up with this kind of function that has a horizontal asymptote at y equals 3, and it tends to negative infinity. But you know what? We just don't have time for that. Who cares? Like, I would look at the there's a nice table of example functions, like canonical functions. Find the one that looks like that, and then do the translations. You flip it over to the other side, and then you increase the horizontal asymptote, and move on. There's my rant about software. All right, 22. Let's do another one just because that was fast. Limit as x tends to 2, f of x equals -4, and limit as x tends to negative infinity, f of x equals negative infinity. Okay, so I'm going to just keep cheating and do the same piecewise function again and again. This is basically the same thing. Same as this one. And I'm going to say that that's done. At some point, I know that Taalman will say explicitly, like, use a continuous function, you smartass. Okay, 23. She may or may not. Limit as x tends to 0, from the left equals the limit as x tends to 0 from the right, and they both equal infinity. So we could just write limit x tends to 0, f of x equals infinity. Alright, I do have one that's like a little bit nicer off the top of my head on this one. F of x equals the absolute value of 1 over x is going to have behavior like this. Number 24. Limit from the left is 3, limit from the right is 1. Whatever, who cares? Limit tends to 5 from the left. As x tends to 5 from the right is 1. Again, piecewise function. Define it in 2 cases. It's either 3 or 1. It's 3 anytime that x is less than 5, and it's 1 anytime that x is greater than or equal to 5. Or it could be undefined at 5, like whatever. You can come up with whatever function you want. These are simple, but boring. That's enough. That's enough for now. We could do an application and a proof next time. thinking forward. There's just a lot of really cool stuff in this book. These are just some practice problems. They're getting kind of repetitive, and yeah, life is too short. So let's just move on. I'm going to mark whatever they are, 21 through 24. We just did 21 through 24. How exciting. Taalman, 21, 21, 22, 23, 24. These are all done. And then I'll clean that up later. So thank you everybody for watching. This was super fun. It's always fun for me. I wrote down a couple of problems from the differential equations book. So if anybody wants to take a look at these and you want something harder, here's Tenenbaum 1.1.1. Radium in a piece of lead decomposing. If 10% decomposes in 200 years, what percent of the original radium present after 1,000 years? Blah, blah, blah. 121, he literally does a similar thing as, what's her name again? Taalman. Defining functions, defining sets, and how would you describe each of these? Like the negative numbers, the non-positive numbers, the numbers between A and B, including B. I don't know. And then later on, we're going to get to these fun types of problems, differential equations. And here, once we get to derivatives, we will see that this function y equals whatever satisfies this differential equation, y double prime plus y prime minus x squared minus 2x equals 0. So we'll see that this function on the left satisfies the equation on the right. So that's where we're going. Differential equations is where calculus is useful and will be applied to the real world, and we can work toward landing on Mars and building nuclear energy. Hopefully we won't build a nuclear bomb in the process. And then theoretical calculus is the wonderful, pristine, ideal world that is completely useless to the real world. But helps sharpen your mind so you're able to land on Mars. Thanks everybody for watching. Name is The Math Hobbyist. Like and subscribe. The Math. If you made it this far, thank you for watching. You must enjoy this. Let me know in the comment section that you made it this far. That would mean a lot to me, because I don't think anybody makes it all the way through one of these videos. It's all a live stream. It's all very rough. If anybody wants to really help support this channel and this entire process, thanks.themathhobbyist.com. You can buy me a coffee there. Just like a one-time tip, $3 if you want to buy me a coffee. I drink a lot of coffee, so I promise you I will use it, and I will use that coffee to help make better content for you. So thank you for watching. I think thanks.works, and I think coffee.works. Or if you want to be lame, you can go to buymeacoffee.com/John Crossley. That's my name. And at least for today, this is the system that I'm using. But I've been trying Patreon, I've been trying buymeacoffee.com, etc. So thanks dot and coffee dot will always work, I think. Thank you again for watching. Like and subscribe. Join the Discord. if you go to themathhobbyist.com, there's a link to my Discord there. Or you can go to discord.themathhobbyist.com. I'm going to put parentheses there because it's not literal tmh.com, but discord.themathhobbyist.com. That's it. Thank you for watching. This was fun. Next time we'll get some scary limits. All right, bye.